Hi, welcome to this video on molecular polarity. So up until now, we've already discussed the polar bonds. So when we talked about that, we talked about how within a bond between two atoms, the more electronegative element has the ability to pull electrons closer to it. And so that ends up creating an uneven distribution of electrons within the bond itself. In this video, we're going to talk about the molecule polarity. So we're going to look at beyond just an individual bond and how the distribution of electrons in the entire molecule are arranged. So one thing that's important to realize is not all polar molecules have polar bonds. So we'll talk about that a little bit more next chapter. But another one is that not all molecules with polar bonds are polar. So a lot of times we have to consider the shape or the symmetry of the molecule overall. So we will look more at Lewis dot structures, and then we'll look at the shapes that the molecules are making, those molecular geometries, to help us identify what's going on with the electrons. So starting off, we've got this concept of a dipole moment. A dipole moment is when there's a separation of charge within the molecule. That's going to happen when your shape and your electronegativities kind of come all together. So we don't always have dipole moments. So for example, like ozone. Ozone is O3. Well, that's a molecule with 3 oxygens that are all the same. So there's no uneven sharing of electrons because none of them have a difference in electronegativity. So my electrons would be evenly distributed and be nonpolar. But in the case of water that you see over here on the right, what we see here is that oxygen is more electronegative. So when I look at the bond that's going on, so the shape, because there was a lone pair, right? So we got to remember that there was lone pairs on here, right? And so these lone pairs are creating a shape that we would call as bent, right? So when we compare this shape and what's going on, I'm going to change colors real fast, we would see that we're really paying attention to this portion of the molecule, right? But the shape creates what we're looking at in terms of symmetry. So when I look at the water molecule, what I see when it's a bent structure is that doesn't have symmetry because I couldn't flip that over and have an identical arrangement. I couldn't cut it down the middle and have it be identical on both sides. And so you'd have to be able to cut it in the plane in all directions, in all possible planes. So we may be able to cut it one way where we just cut it this way, like straight horizontal, the way that picture is, and that might look like it. But what I can't do, and I'm going to back that up a little bit, what I can't do is I can't cut it vertically and have it be the same. So that's not going to be a possibility. So what we want to do, so that indicates there's an asymmetry or the molecule is not symmetrical. So that means that if we have polar bonds, there's a good likelihood that those polar bonds create an uneven distribution of electrons. So let's look at the bonds themselves. So when I look at the bonds between the hydrogen and the oxygen, we know that the oxygen is more electronegative. So I know that these bonding electrons are actually going to be shifted more towards the towards that oxygen, and I'm trying to draw it on this little bitty picture and it's not coming out very nice, but my electrons in the bond are going to be shifted more towards the oxygen on both of those scenarios. And so what ends up happening is I have more electron density in this oxygen area near that atom, and I've lost some of that electron density in the hydrogen, or it becomes electron deficient. So it's not a complete loss. It's still sharing the electrons, but it's not sharing them equally. So what we say is the hydrogen becomes partially positive because it's lost some of the negative density that's associated. So that's a little partial sign. It's lost some of the electron density that's associated to the electrons that are negative. And then my oxygen is going to become partially negative because it's gaining those negative electron density. But not a full-on charge like an ion, just enough to give it a positive or a negative side. And so we can see water as an example over here is 2 lone pairs will establish a really strong negative pole. Ammonia, which is NH3, ammonia has a lone pair, which is also going to give it a pretty strong negative pole. the biggest thing is the direction of the arrow that indicates the dipole moment is always, so notice how you see this little arrow right here that they drew. The direction of that should always point towards the negative pole, or where the electrons are going, towards the more electronegative element. And then you'll notice that the back side looks kind of like a little positive arrow. That helps remind you that that's the positive pole. All right, so here's an example. If the octet rule is obeyed and all of the surrounding bonds are the same, then the molecule would be nonpolar. So nonpolar if all the surrounding bonds are exactly the same, because all the dipole moments are going to cancel out. So even if we have polar bonds, right, in something like carbon dioxide, so if we look at carbon dioxide right here, it's going to be nonpolar. So it does have polar dipole moments individually, but overall it does not. They're going to cancel each other out. So this is where it talks about, if you're in physics, right, the dipole moments have the vector quantities. So if I pull one direction with a force and I pull the other direction with a force, then those two forces, and they're equal, then those two forces are going to cancel each other out, right? So that's what it means by vector quantities. So when I look at this one, what I can see is that this is symmetrical. I could divide it any direction and it would be identical, right? So even though when I look at this and I see that the oxygen's more electronegative and I've got individually polar bonds, we're pulling evenly in all directions. So that means that those dipoles will cancel. So there's no dipole moments overall. So this is going to be considered nonpolar. So if the molecule ends up being symmetrical like that, then you're typically going to have a nonpolar molecule. The only time it wouldn't be would be like, this is oxygen and then this was like nitrogen or something. Then they're definitely not going to be pulling equally, and then you don't have a symmetrical molecule anyway, so it wouldn't matter. All right, so then we can have methane. So here's an example with methane. Methane is a tetrahedral structure. So with methane, what we're seeing here is, and this one's a little harder because you have to see it three-dimensionally, but remember that when we're looking at this like what methane looks like, right here, this is pulling up directly, right? This is a tetrahedral where it is polar. This is one on the left is one where it's not. So this is pulling up, but then this is pulling backwards, this is pulling forwards, and this is pulling to the side. So we're pulling evenly in all directions. So a tetrahedral in all directions usually is going to be nonpolar. In this case, C to H is nonpolar anyways. Those are nonpolar bonds anyways. So right away, we wouldn't have had any polarity in our bonds. So that would have been a huge indicator that the molecule itself was going to be nonpolar. Now, another example, though, in which there is always those weird exceptions. So this portion of my molecule is nonpolar, but do you see that there is the carbon in the middle to the chlorine? There's a polar bond right there. There's nothing to break that apart. This is an asymmetrical molecule. So since the molecule is asymmetrical, there's nothing to pull that apart or to basically counterbalance this upward charge. So we would see partially negative up here, and then that carbon would be partially positive. And let me change colors on that so you can see it a little better. But so this would be partially negative, and then your carbon would be partially positive because it's losing a little bit of the electron density. So this is asymmetrical. So as a whole, this is a nonpolar. This is kind of the type of molecule. This is a little bit small, but when you look at the fatty acid chains that are making up the phospholipid bilayers, right? When we look at the phospholipid bilayer in biology, part of that membrane that makes up the cell membrane, that whole purpose of that membrane is one side is polar and one side is nonpolar. So this is where that kind of ties in. So you've got this nonpolar side, which is those hydrogen carbon sides. Those are nonpolar chains. And so in the phospholipid bilayer of the cell membrane, those are like nonpolar, so they're hydrophobic. They don't really like anything because they're not polar. But then you've got the phospholipid part, or the phosphate groups. That side is going to be hydrogen or water loving because it's going to be polar. So this is what you kind of see, but in larger quantities with those fatty acid chains. All right. So another example, I don't know why I just accidentally drew that line. So another example you'll see is if the octet rule is obeyed and there's a lone pair on the center. So this is when we end up with stuff that is polar versus nonpolar. Oh, and you know what I just realized? I wrote nonpolar up here, but it really was polar. My bad. So go back and make sure you erase that in your notes. I'm just made a mistake. It won't let me erase it either, so we're just going to write over it because I went too far back. This is polar, right? That portion, that asymmetrical portion is polar. The bottom portion was nonpolar. Okay, so this example is talking about the methane, or the ammonia that we were talking about earlier. So ammonia, NH3, right, has that lone pair, and it looks like this, right? We've kind of done this a couple times. It gives us that trigonal pyramidal shape. So same kind of idea when we think about its structure, it's not going to be symmetrical. So there's no way for me to cut that in half or in half and make it symmetrical. So this is going to be considered asymmetrical in shape, right? So as soon as we put that lone pair on the central atom, a lot of times it changes the symmetry. So that's asymmetrical. And so then what we see happen here is that there's no way for the cancellation of the electron density. So the electron densities don't cancel each other out, or those vectors, if we think of it that way. So what we end up seeing really is we see that we're pulling electron density. I drew it the wrong direction. I'm really struggling today. Let's go back. All right. So with electron density, what we're seeing is the nitrogen's more electronegative. So we're pulling electron density towards the nitrogen in all of these. So when we do that, our hydrogen becomes partially positive because it's losing some of that electron density. It's not losing the bond, though. It still claims them. And then your nitrogen's becoming partially negative because it's gaining that electron density. So when we look at this overall, that's going to be a polar molecule. And so what we can see is that those polar bonds contributed, and the shape of the structure contributed to it becoming polar overall. So what we see is that overall bond picture. So ammonia is polar since the lone pair is pushing the hydrogens away, and it creates that asymmetrical molecule, and the dipoles would add together instead of canceling out. And they're adding together and focused upward. Okay, so here is another example. So this one wants us to draw these different structures. So if I draw CH4, that's just a straight tetrahedral, right? So we've got the 4 hydrogens, and I'm drawing them somewhat like the shape would be for tetrahedral. And then the CH3, we saw that one a minute ago. That's a chlorine going up, and then the 3 hydrogens coming down. And then we can have CH2, so that's going to be a C with the chlorine, and I'm not drawing the full dot structure, but I guess I should, because that makes a difference of whether or not they end up double bonding, right? So we've got the 2 hydrogens, and then we've also got a carbon with 3 chlorines, Cl and Cl, all right. And then the last one is, I'm going to squish it in over here, but hopefully you're able to draw them a little smaller than me, but I can't, I struggle to fit them all in, with all 4. So when we look at this one, all right, let's look at each one individually. So when I'm looking at these structures, right, I can see that this is nonpolar overall. Because carbon, hydrogen, so in this first structure, that's going to be nonpolar because overall, the CH is nonpolar. So CH bonds are nonpolar, so there's no option, okay? So if I don't have any polar bonds, then there's no uneven distribution there. On this one, we already talked about this, but we know that chlorine is pulling upward, right? And so that is going to become polar. So on that one, we got a polar molecule. It does have a side that is nonpolar, but overall it's polar if we look at the whole thing because there is that polarity. So this would be partially negative, and then that's going to be partially positive. So then we look at this one. We're pulling this way and we're pulling this way. So in that case, again, we're going to see that that's going to be polar, right? And we're going to see that this side, this is going to be partially positive because it's losing electron density, and these are going to be partially negative. Very similar to what we see in the water molecule. Then we've got 3, so we're pulling this way, and this way. So this one also is going to be asymmetrical because we've got that one side. So this is also polar, okay? And again, this is going to be partially negative, partially negative, partially negative. The way I drew it, it looks flat, but remember it's not. There's part going back. And then your carbon becomes partially positive. Now this is where it gets crazy. So we have these polar bonds. So all this time we've been saying these are polar bonds. But now when I look at this one, because there's symmetry, even though there's polar bonds, right? There's symmetry. We're pulling equal in all directions. And so we're pulling in the X, the Y, and the Z direction all the same. So this is actually going to become nonpolar because all of those are going to cancel out. So it has polar bonds just like we saw in the last 3 of those compounds. The difference is that all 4 of those bonds in that tetrahedral structure are identical, and so therefore that's going to create symmetry, and that's going to end up making it nonpolar. All right, in this next one, for each of the following molecules, show the direction of the bond polarities and indicate which ones have a dipole moment. So it's giving us HCl, and that should be a lowercase l, but whatever. So we're going to have H bonded to Cl, and so my structure would look like this. And then I'm going to have Cl bonded to Cl. It's going to look like this, right? And then I'm going to have, and it kind of is helping you out a little bit, but we've got SO3. I feel like I'm going to run out of room here because I did too much space. So with SO3, I have to do this in my head. I've got 24 electrons, so that's 12 pairs. So 3 of those pairs are this, and then that means that we're going to have 9. All right, so we're going to end up having a double bond. This one would actually exhibit resonance. Take off one of dots. So this would actually exhibit resonance when we look at that structure because that lone pair or that extra bonding pair could rotate around. And then I've got CH4, which we've already drawn up here, so I'm not going to redraw that one. So that's the CH4. I already drew that one up at the top. And then H2S, which that's going to end up being 2 lone pairs on that center atom. So remember, that creates a bent structure that's going to push those down. So when I look at this one, or look at all of these individually, let's look at them to see what we would come up with. All right. So first, we want to show the direction of the bond polarities. So this is only one bond polarity, and we know chlorine is more electronegative, so I'm going to pull towards chlorine. Okay. And then overall, that's going to have a dipole moment. So would this be polar or not? And I would say yes, this is a polar molecule. Okay. All right, let's look at C to Cl, Cl to Cl. That is going to be nonpolar because there's no bonds that are polar. So those are going to be a nonpolar molecule as a whole because the bond isn't polar. On this trigonal planar structure that we see for SO3, because it's so nice and symmetrical, we're going to pull, so we would pull towards the oxygens, right? But this is going to cancel out. So this has symmetry, and so therefore this is nonpolar overall as a molecule. So hopefully that makes sense. Then I look at, we've already talked about the CH4 up here at the top being a nonpolar molecule overall, because again, no lone pairs on the center gives it symmetry, and all the bonding atoms are the same. Then we have the H2S. On H2S, we're going to see the sulfur be more electronegative. Not by a whole lot, not as much as it is for oxygen, because sulfur, I think, has an electronegativity of like 2.8, and hydrogen is 2.1, so that's a small electronegativity difference, but enough for us to count it. So then this is going to be partially negative, and then my hydrogens become partially positive. They lose a little bit. So this is a polar molecule. So again, it's not symmetrical. So since it has those lone pairs on the center, it creates an asymmetry, and then that's going to create the molecule to be polar because it won't cancel out. All right, so exercise 14 says because of the noble gases have filled s and p valence orbitals, they were not expected to be chemically reactive. In fact, for many years, these elements were called inert gases because of their supposed inability to form compounds. However, in the early 1960s, several compounds of krypton, xenon, and radon were synthesized. That's because remember that they have d orbitals. Since they have d orbitals, they can have expanded octets. So, for example, a team at the Argonne National Laboratory produced the stable colorless compound, xenon tetrafluoride, predicted structure, and whether it has a dipole moment. So when we look at its structure, it wouldn't matter which one I draw. So if I draw it as let me see, draw. So let's say I've got two options, so I can do a formal charge on this one. So xenon, I could have xenon. It's going to be 4 either way. So I'm going to have F, 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 and F. All right, I'm going to add up all those valence electrons. So that's going to be 8 plus 4 times 7. So 28, so that's going to be 36 electrons. All right, that's 18 pairs. I just drew in 4, so that's 14 lone pairs. So when I start filling in my lone pairs, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13 and 14. So that's that expanded octet we talked about. So fluorine being a halogen, so small, can't have an expanded octet. So, and xenon already has an expanded octet with this structure, so we wouldn't double bond or anything like that. This gives it 6 valence. It's probably happy with that. If we checked formal charge, we probably could do a different structure, but fluorine really wouldn't prefer, those halogens really do not prefer double bonds. They prefer single bonds. So this is probably a more stable structure. So then this structure, when we look at this, in terms of what our shape is, right, we have those lone pairs on the center. So this is actually, for electron geometry, we would say that this is octahedral because we've got 8 pairs of electrons somewhere around the center. So that's an octahedral electron geometry. But what we want to remember is that in this structure, we wouldn't see these. So that would be, when those disappear, what we end up getting for the molecular geometry is going to be square planar because they're going to just be flat. So it's really just a flat structure. I know it's hard to picture that, but it's flat and they're in all 4 directions. And so what we're going to see when we look at the fluorine being very electronegative, right? I'm just going to draw kind of a little square here, right? We're going to pull towards the fluorine, towards the fluorine, towards the fluorine. So what we're going to see is, in this case, all of those polar bonds are going to cancel out. So overall, this is going to be a non-polar molecule. So this is a perfect scenario in which there is a lone pair on the center. Those lone pairs on the center, you want to be careful with because you want to look at the whole structure to see if it's going to change. So that molecular geometry helps you see that a little better than just being like, oh, there's a lone pair in the center, it must be polar. That's not the case always. So look at the structure, see if it has symmetry when you draw the molecule shape. So you have to take into account the molecular geometry when you do this. All right, next, exercise 15. Predict the molecular structure of the sulfur dioxide molecule. Is the molecule expected to have a dipole moment? So when we do sulfur dioxide, so same scenario. I've got S and I've got O and O. So I'm going to draw it. So I've got 18 electrons. Divide by 2 is 9 pairs. And I already drew in the 2 sigma bonds, so that's going to leave 7 lone pairs. All right, so with my 7 lone pairs, that's going to put a lone pair on my center sulfur. So I know what that's going to do, and I'm going to erase and actually redraw because I want to show that there's going to be a lone pair on the center. I want to show my shape with this. And I know that as soon as I put a lone pair on the center, that's going to push those bonds down, and I'm going to end up having a double bond. This would exhibit resonance. because that double bond could move in other locations, but I don't need to identify the resonance to make sure that I'm showing to show the structure, figure out polarity. So this would have resonance, and you would, if it asked to predict that, then you would have included both structures. So then on this one, what we're going to do is we're just going to look at my bonds. So I know sulfur versus oxygen. Oxygen is going to be more electronegative. So my electrons are going to pull towards the oxygen. Notice it's pulling away from the central atom instead of towards it now. And so that means the sulfur is going to be partially negative or partially positive. It's losing some of that electron density. And my oxygens are going to become partially negative. All right, so when that happens, this would have a dipole moment overall. So you could always draw, like sometimes you'll see them draw the big, you saw it on some of the other pictures, that there's an overall dipole moment going towards the oxygen side of the molecule. So this is a polar molecule for sure. So one thing that's really neat, and we're going to talk about this, is a lot throughout the years, understanding polarity is we're going to be discussing why, like different states of matter, and so why does water like itself, but why does carbon dioxide gas not like other carbon? Why is it normally a gas at room temperature versus a liquid or a solid? And a lot of that has to do with the polarity of the molecule, in addition to the energy within the molecule and the temperature that it's at. But we're also going to talk about solubility later and why some things dissolve better than others. So polar molecules have those dipole attractions, and so they can attract to other things that are also polar. That also means that they attract very well to themselves. So next chapter, when we start talking about states of matter, we're going to talk about intermolecular forces, and polarity is going to be really important because the polarity is used to determine that. All right, so that concludes this video on molecular polarity. So remember, one thing you want to do, draw the Lewis dot structure and make sure you do it correctly. Then you need to look at what the molecular geometry is, because the molecular geometry is going to help you determine if the polar bonds are going to cancel or not. So you need to have a correct Lewis structure. Look at your polarity of your bonds and then see if they cancel out. So if your structure is symmetrical, then the polar bonds would cancel. And if they're not symmetrical, then polar bonds will not cancel. So that'll help you determine if it's polar or nonpolar. So there's a lot of steps involved to figuring out polarity of different molecules.